Okay, so now we're at section 8.6, which is called three-phase generator. And we worked our way up to this point. We started with a single-phase generator, and then we moved to the two-phase generator. We noticed with the single-phase generator that the power output um, is half of the peak power. We noticed with the two-phase generator that the power is constant and it is equal to the peak power of one phase. And now we're going to move on to the three-phase generator. And we're not going to get the doubling effect. And, we won't necessarily get into the math of this, but we will go from twice the power, but, single phase to two phase, double the power, two phase to three phase, we're going to increase the power output by 1.5. So we're going to walk through that, look at the construction of this, define some terms, and move from there. As we look at the construction of the three-phase generator, we see that it follows the scheme of the earlier generators. And still, you remember the very first one, we looked at phase one, which was labeled as A1, and then phase two. But now in the two-phase generator, this was 90 degrees, placed 90 degrees between, so now what we're seeing is from A to B is 120 degrees. So if we say this is 0 or 360, whatever we want to say, and then to move from B to C, we go another 120 degrees to 240 degrees, to make that complete circumference around there. Now, because these are placed mechanically at, let's see, what am I trying to do here? Because these are placed mechanically at 120 degrees difference, the outputs from the induced voltage by the rotating magnetic field is also going to be 120 degrees. So I think I have a better representation of that, something that's a little clearer. Let me bring that up for us to look at. So here's I think a better representation of the three phases of electricity. And what we're seeing here, when we look at this, is we're seeing a representation that shows, this would be phase one, or A, and it starts at 0. And then what we see from this, and it's marked down here, right? If we looked at the difference between phase one and phase two, we would see that there are 120 degrees separation between the two. Okay, so to go from the peak, and the peaks or zeros are good places to look at curves, right? So if we look at the peak of phase one to the peak of phase two, it's 120 degrees from there. So if this is at 90 degrees, right, then we're going to add 120 degrees to that. So this would be like what, 210 degrees, and then so forth and so on. But here's phase two, and phase two peaks at this point, and phase three is going to peak 120 degrees later. So, whereas we were looking at with the two phase, these 90 degree separations, now we're looking at 120 degrees of separation. And the reason, again, is because mechanically, when we build the three-phase generator, we separate the three coils around 360 degrees. 3 into 360 is 120. So mechanically, it's 120 degrees. Electrically, it's 120 degrees. And so now back to our textbook, and we can see, we can see those points on the graph, again, and the 120 degree separation, and that just remains a constant through this whole thing, and that relationship is maintained throughout. Then if we wanted to represent this same thing with the use of vectors, or as we talk in terms of electricity, we talk about phasors, but so, here's EA1, and here's EB2, and here's EB3, and we can see from that, of course, this 120 degrees separation through that process. Okay, so all the different, looks at this thing, the actual physical construction here of the generator, the look at the output voltages in terms of the sinusoidal outputs that are created, and then that same representation in terms of its vector notation, noting the 120 degree separation between those. Now, one other quick notation here before we move off of this, and this is actually on page 162. It's sort of a side note, and we have this term phase, and a big part of electrical studies is understanding the language, and so phase is used in so many ways, and there's 11 different listings of the term phase there on page 162. And like Wilde says in the text, you have to look at the context with which it's used. You'll see, like he says, out of phase. Okay, so when we just looked at this three-phase generator, the waveforms were 120 degrees out of phase. Or we might look at the voltage and the current relationship and being out of phase, because of capacitive or inductive loads. Three phases, when you're talking about three phases, that's what we just finished the discussion of. Phase to phase voltage. When we get into three-phase electricity, we make our measurements from phase to phase, unless we're told in another instance to measure from phase to neutral. And we'll get into all that as we proceed through this. A phase sequence is the order of the phases. A burned out phase talks about, a damaged three-phase generator. Three-phase currents, phase shift transformer, phase-to-phase fault. The phase-to-phase fault would be, between, say, the three phases, and there was some sort of fault, and that occurs sometimes with power lines, where a branch might drop across and short out between phases. And there's a phase to ground fault. We always have this neutral, and sometimes you'll have a phase to neutral fault. So it all depends on how it's used in context. And what I'm saying is, don't get confused in terms of the many uses of this term phase. It has to be looked at in terms of what the context is.